This content is covered on pages 254 through 259 of your textbook, and it's meant to help you achieve learning objective number 38, which is to define prevailing wind and explain how wind direction is described. Be sure to skim those pages before watching the video and read the chapter carefully before attempting any online quizzes. When the wind consistently blows more often from one direction than from any other, it's called a prevailing wind. You may be familiar with the prevailing westerlies that dominate mid-latitude circulation. In the United States, for example, these winds consistently move the weather from west to east across the continent. In mountainous areas, winds are often complex, and the available wind data are limited, and they provide very little information on wind direction. Trees have been used for hundreds of years as an ecological indicator of wind direction, wind exposure, and as a measure of the severity of wind and ice damage. One technique for determining the mean wind direction, called tree flagging, uses the wind-blown structure of trees near the tops of mountains to estimate the prevailing wind direction of the strongest winds. Although the strongest winds may only occur during part of the year, seasonal variations in the wind direction can have a pronounced effect on the type of tree deformation. So techniques have been developed to assess the annual wind speed using measured effects on two widely distributed species of conifers. Trees can provide a simple, inexpensive, and quick method for identifying promising locations for things like windmills, and also for other reasons, where you might want to understand the wind potential of a region. The term wind throw refers to trees uprooted by wind, and wind throw is common in all forested parts of the world that experience storms or high wind speeds. The risk of wind throw to a tree is related to the tree's size, the height, and the diameter, which is known as the sail area, and the anchorage provided by its roots, but also the exposure it has to the wind and the local effects of climate on the wind speed. So a common way of quantifying the risks of wind throw to a forest area is to model the probability or the return time of a wind speed that would damage those trees at the location. Tree senescence can also be a factor, where there are multiple factors contributing to the declining health of a tree. That can also reduce its anchorage and increase its susceptibility to wind throw. So the resulting damage can be a significant factor in the development of a forest, especially in an even-aged stand. Imagine trees that usually don't grow from seeds, but they grow from nurse logs. When the mother tree falls over, a whole new batch of young ones grow up orthogonally or at right angles to the trunk. All around the marshes of the mid-Atlantic, we have trees which are called white oaks, and they do not like salt water. And so when they get salt water in their roots, they tend to get a little bit weaker. So we think that we can see a signal of rising sea level, making even-age stands of white oak more susceptible to this kind of damage. But wind throw can also increase following logging or changes in land use, especially in young forests that are managed specifically for timber. The removal of trees at a forest edge increases the exposure of the remaining trees to the wind, and trees that grow adjacent to lakes or other natural forest edges, or in exposed situations like hillsides, usually develop a greater rooting strength to prevent the tree throw from happening. And that's a feedback mechanism back and forth between the wind movement and the roots of the tree. So in other words, the tree is adapting or adjusting to the climate. Acclimative growth is what we call that. If a tree doesn't experience wind movement during the stem exclusion phase of the forest's growth, it's not likely to develop a resistance to the wind. So when a full or partially developed stand is cut by a new road or a clear cut, the trees on the new edge don't withstand the wind as well. You can see this on a construction site near Snoqualmie, where the builders were supposed to leave a zone of the forest aside. This is a buffer zone, and it clearly wasn't wide enough, but you can see a number of trees falling into the forest in the direction of the prevailing wind. Winds are always labeled by the direction from which they blow. A north wind blows from the north towards the south, and east wind blows from the east towards the west. One instrument commonly used to determine wind direction is the wind vane. You often see one of these on top of buildings, and sometimes the wind direction is shown on a dial connected to the wind vane. But the dial indicates the direction of the wind either using points of the compass, so north, northeast, east, southeast, and so on, or by a scale of 0 to 360 degrees. In the latter scale, 0 or 360 is due north, 90 degrees is east, 180 is south, and 270 would be west. Even though weather systems generally track from the west to the east in the United States, pressure centers have either clockwise for high pressure anticyclones and counterclockwise for low pressure cyclones. As a result, the winds associated with the westerlies, as measured at the surface, often vary considerably from day to day and from place to place. But every public airfield in the world should have Arabic numbers painted at each runway end, aligned predominantly to take advantage of prevailing winds. So many airports have a range of runway configurations to accommodate changes in seasonal winds, but the runways are numbered based on the magnetic azimuth in which a runway is oriented. So there are 360 degrees on a compass rose. Runway numbers are determined by rounding the compass bearing of one runway end to the nearest 10 degrees and then chopping off the last digit, meaning that runways are really numbered from 1 to 36. I don't think there are any 0 runways out there. But the opposite end of the runway should be the 180 degree opposite direction. So it's numbered 18 higher or lower. What should the number at the other end of this runway be? Subtract 18 from 27 to get 9. With one end at 90 and the other at 270 degrees, this is oriented east and west. So if you can see a numbered runway in the air photo, you can tell which way is north. That's just a little tip about air photo interpretation. You might be thinking that the numbers on this diagram are backwards. On a handheld compass, south is 180 degrees, so 18 in runway terms, and west is 270. But the W is numbered 9 because the runway number is connected to the direction that the plane is traveling in. So if you're on runway 9, when you're heading east, 90 degrees on a compass, runway 36 means you're moving north. and so on. So the next time you travel by airplane and the pilot announces you'll be taking off on runway 27, I don't think that really happens, but you'll know that you're traveling due west. By the way, aircraft carriers do not have runway designations painted on the flight deck. Instead, the ship turns into the wind when the jets are taking off or landing. A windrose provides a way to represent prevailing winds by indicating the percentage of time the wind blows from various directions. The length of the lines on the windrose indicates the percentage of time that the wind blew from that direction. So as you can see in this figure, the direction of airflow associated with the belt of trade winds is much more consistent than the westerlies. That's in this picture of North America. But knowledge of the wind pattern for a particular area can be useful. For example, when you are constructing airports, the runways have to be aligned with the prevailing wind to assist in takeoffs and landings. Further, prevailing winds greatly affect a region's weather and climate. Mountain ranges that trend north and south, like the Cascade Range, cause the ascent, the rising of the prevailing westerlies. So the windward or west slopes of the ranges are dry. Or are wet, while the leeward side, the east sides, are dry. Wind speed is measured often with a cup anemometer, which has a dial much like the speedometer of an automobile. So you can see in the picture on the right, there's a cup anemometer. Sometimes an arrow vane is used instead of a wind vane and cup anemometer. That picture on the left is an instrument that looks like a wind vane, but it has a propeller on one end. That keeps the propeller facing into the wind and allows the blades to rotate at a rate that's proportional to the wind speed. So if the wind is fast, the propeller spins fast, and you make a mathematical adjustment to figure out the exact wind speed. That instrument is commonly attached to a recorder that produces a continuous record of wind speed and direction. And the information from a lot of these sites is available for determining locations where winds are steady in speed and direction. And that helps improve weather forecasts, including hurricane monitoring. Measuring the speed and direction of winds aloft is also important. Upper level flow can be established using satellite images to track cloud movements, and also things called Rawlinsons, which are radiosondes that are tracked by radar. Those allow you to calculate airflow at several levels of the atmosphere. Use the content provided on the Canvas site, as well as outside internet resources, to verify that you can answer these questions. And if you can comfortably answer them, you're in great shape for the final exam. If you can't, then reread the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.